Welcome back to the discussion of spatial networks, in particular the query languages for spatial networks. In past few videos, we have looked at the motivation for spatial networks such as the navigation apps that we all use on smartphone. We also looked at conceptual models such as entity relationship diagram as well as graphs. Graphs have nice mathematical and computational properties. And we also discussed why the query languages we know so far, particularly one from the previous chapter, are not adequate. So we need to learn new statements. We did learn one new statement, connect by, which was in last video, and this video we are going to learn another one called with recursive, which is part of SQL 3 standard and widely available through products. Okay. So at the end of this video, we should all be able to describe this recursive or with recursive statement in SQL 3 and also use it to query graphs. Okay. So here is a quick background. Again, formally, you remember that the special query languages that we studied earlier were simple. They were based on relational algebra and some user-defined data types. And they, at least the relational algebra based old SQL could not compute transitive closures or shortest path. Okay. So we needed to extend SQL, and people can do it in different ways. One could add new abstract data types. Now OGIS data types such as points, polygons do not include graphs and paths. Okay. They do not include operators like shortest path. But if we were to design new abstract data type and add it to SQL 3, that could support graph kind of queries. The other option is to use custom statements. We learned one of those in the last video, the connect, and we are going to learn with recursive in this video. Okay. So without further ado, let's look at the inputs and outputs of with recursive statement. In terms of inputs, the first input is similar to the one for connect, which is the graph. Okay. So we need to have a table which represents the edges of a graph. Okay. So for example, this set of edges may represent a graph of this kind, where let's say node 1 to 2 there is an edge which is the first row and so on. Okay. Now given that the output is a transitive closure, so we can compute predecessors, successors and so on. Okay. But in terms of inputs, with recursive actually takes two additional subqueries. So in other words, it's a nested query. The first subquery describes ways to initialize the result. So we can take this table R as an input and say that the result may be initialized with this table itself or a subset of rows from the table. The second query explains how to grow the result. So starting from some basic values which is specified by the initialization query, how do we add more rows to the result? Okay. So using these facilities, you can compute predecessors, successors, and you can actually do a little bit more. You can also go ahead and compute shortest path and things of that kind. Okay. So to give you a quick example, here are the three parts of with recursive statement, and we'll illustrate each. So the first part usually is the name of the result table and the columns in the result table, and that follows the keyword with recursive. So in this case, the result will be a table named X, and this table has two columns, source and the other column is destination. So the table structure is pretty much similar to the input that we saw before in this case. But if you wanted, we could have other structure. For example, you could choose only one of these columns as we saw with the connect statement. The second part is a subquery which tells us how to initialize the result named X. So in this case, this query is something you have seen before. So if you only concentrate on the SQL query inside the blue box, then you can probably tell that the result is initialized by simply copying this input edge table R. Okay. The third part is the recursive query. So given some initial result, how do we grow it? And it is shown here, and notice that this is a recursive query. So some of you have done recursive programming in computer science before or in mathematics, and essentially recursion means that you are defining something using the same thing. So for example, here result X is being defined, but notice that the part of the definition uses X, right? So this result X is defined in terms of itself, and that's called recursion. So let's at least look at this example to understand how it works. Okay. But in all recursions you have to have a base case, and that's this blue part, in order for this recursion to end. Okay. All right. So we at least now saw the syntax, and in this syntax really if you build on your old SQL knowledge, then there is only very little new part. The new keywords were with recursive, you followed the result table name and its columns. Then there was another keyword as, then you followed with a SQL query to initialize the results. Then this union operator is also something we know from before, it just takes two tables and merges them. And then there is a last part which is another subquery, which is a select statement to grow the result. Okay. So let's look at an example input and output, and then we can see an execution trace to appreciate it even more. So example input could be a simple graph which is shown here with 5 nodes and 5 edges, but it's represented in a tabular form that's shown on the right as table R. Okay. The output, so this is sort of your input. The output X is another table which has 2 columns. So in this case, your output table is shown here. It just happens to have source and destination columns specified here. So it's very similar to input in this case. And graph theory perspective, it is actually a richer set of edges. So if I can reach node 4 from node 1 via multiple other edges, then there is a direct edge from 1 to 4 here, okay, as we discussed in transitive closure. All right, so let's take a look at the meaning of this statement, and one way to specify meaning is via providing a hand execution procedure. Okay. So in order to compute result X, we start with the initialization query, and if you remember the initialization query, it was simply copying source and destination columns from input table R to result table X. So if we did that, then these 5 rows from the input table will get copied to the output table X. Okay. Once we have done that, we are going to grow the result using the recursive step. So again, recall what the recursive step was, and in recursive step we tried to match the destination column of input table, that's this column, to the source column of a result table. So as long as there is a match between destination here and source in the result, we can add new rows. Okay. To rephrase it, we can say it as follows. We can say that in case you had a row AB in R, okay, such as let's say 1, 2, and you had another row BC in X, such as this, let's say 2, 3. If that happens, then you can essentially say, look, in the original result we can go from 1 to 2, and in result table we can go from 2 to 3. So we can add a row from 1 to 3 in the result table. Okay. To give you more specific example, here it is. Okay. So R has 1, 2, X has 2, 3, right? R has 1, 2 and X has 2, 3, and in this case R's destination matches X's source. So we could add a new edge 1, 3 to result, okay, and that's shown as here. So we added one more. Okay. We can find similar other pairs from R and X to add more information. So for example, you notice that in input table you had 2, 3, and its destination matched the source of 3 to 4, and when that happens, now we can add 2 to 4 in the result. Okay. So continuing on, you can find other such pairs. R has 5, 3, X has 3, 4, so you can add 5, 4, and then finally R has 1, 5, X has 5, 4, so you can add 1, 4 in the result table. Okay. And if after this, if you try this procedure further, in this example we are not going to get any. So this recursion continues till the result stabilizes. If we cannot add any more, then the recursion ends, and at that time you have the full result. So this is your result table in SQL. If we want to visualize it as a graph, then it will look like this transitive closure graph that we saw before. And all the new rows we added are these new edges that show up in the transitive closure. Okay. So to summarize, in SQL 3, a new statement with recursive was added to support graph queries such as predecessor successors that we saw before with connect by, but also newer queries like shortest path. And in this particular video, we saw the syntax of with recursive. It essentially names the result table and its columns. It gives you an initialization subquery, and finally a recursive subquery to grow the result. Okay. And this gives you a basic means to write queries on the graph in SQL 3. With this, we'll more or less wrap up the discussion of query languages on graphs. And in subsequent video, we will come back and go to the physical data model, try to see the data structures which are used to represent these graphs, and also the actual algorithms that a database may keep to quickly execute graph queries on large graphs. Okay? So look forward to seeing you in the next videos in physical data model. Thank you.